Hello, Stormwater designers, and welcome back to Clear Creek Solutions hydrology education videos. Today, we're going to be doing a video on urban flooding, explaining the causes, what are some of the issues going forward as it relates to urban flooding, and what can be done to improve this phenomenon that's occurring really worldwide. Before we get started, we have a free EPA swim course that you guys should check out in the description down below. It's free to help you get started using the model, featuring over 20 of our tutorials. Anyways, so urban flooding refers to flooding that occurs in developed areas when rainfall generates runoff faster than drainage systems can convey it. FEMA distinguishes urban flooding from riverine flooding, which occurs when rivers overflow their banks. In urban flooding, water may accumulate in streets, parking lots, and low-lying developed areas even when nearby rivers remain within their banks. Key driver is the interaction between rainfall intensity, impervious surfaces, and a drainage system capacity. So understanding this interaction requires both hydrologic and hydraulic analysis, which we're going to explore in this video here. So what is urban flooding? Urban flooding typically results from one or more interacting factors. High intensity rainfall can produce runoff rates that exceed inlet and pipe capacity. Impervious surfaces such as pavement and rooftops reduce infiltration and increase runoff volume. Drainage systems are designed for specific performance levels and may not accommodate storms. Beyond those criteria, blocked inlets or debris accumulation can reduce effective capacity. Additionally, downstream boundary conditions, such as elevated river stages or tidal influence, can reduce system discharge efficiency. These combined factors create conditions where runoff accumulates faster than it can actually drain. The hydrologic component of urban flooding relates to how rainfall is converted into runoff. According to EPA and NRCS guidance, impervious surfaces reduce infiltration and increase direct runoff. Urbanization typically shortens watershed response time because runoff travels faster over smooth connected surfaces. This reduction in time of concentration generally increases peak discharge for a given storm, assuming rainfall intensity increases with shorter duration. Watershed slope, soil type, and land cover all influence runoff generation. Hydrologic modeling estimates how much water enters the drainage system during a particular storm. So the hydraulic component concerns how runoff moves through pipes and channels. Conveyance systems have finite capacity determined by diameter, slope, roughness, and boundary conditions. When flow exceeds pipe capacity, water levels rise and systems may surcharge, meaning they operate under pressurized conditions. Backwater effects from downstream water levels can further reduce effective capacity. Flow control structures such as weirs and orifices also influence hydraulic behavior. Hydraulic modeling evaluates whether infrastructure can convey runoff without exceeding acceptable performance criteria. So extensive research, including USGS and NRCS publications, has documented that urbanization increases both runoff volume and peak discharge. Replacing vegetated land with impervious surfaces reduces infiltration and surface storage. The resulting hydrograph typically shows higher peaks and shorter duration compared to undeveloped conditions. This phenomenon is often referred to as the urban hydrologic response. The degree of change depends on the extent of impervious coverage and drainage connectivity. Storm drainage systems are typically designed for storms of specified statistical frequency, such as 10-year or 25-year return period events, depending on local standards. This means infrastructure is not intended to prevent flooding under all possible storms. Engineering design standards often use risk-based criteria, accepting that exceedance events may occur. In many jurisdictions, minor street flooding during larger storms is anticipated and accounted for in design philosophy. Understanding design criteria is essential when evaluating flood performance. Rainfall intensity, duration, frequency, or IDF curves, which we have a separate video on that you can find on our channel, are used to characterize storm intensity statistically. Urban drainage systems are particularly sensitive to short duration, high intensity rainfall because these storms produce high runoff rates over short periods. It is important to distinguish rainfall depth from intensity. Depth describes total accumulation, while intensity describes rate. Peak runoff is more sensitive to intensity than total depth. IDF characteristics vary regionally, so local rainfall statistics are essential for accurate modeling. Hydrologic modeling tools estimate runoff generation. The rational method is commonly applied in small urban catchments for peak discharge estimation. The NRCS curve number method estimates runoff volume and hydrograph shape based on land use and soil conditions. Continuous simulation models, including EPA-SWMM, represent rainfall over extended time periods and allow infiltration recovery between storms. Accurate watershed delineation and appropriate parameter selection are essential for defensible results. Hydraulic modeling evaluates how runoff moves through conveyance networks. One-dimensional pipe networks models simulate flow, depth, and surcharge within defined conduits. Dynamic wave routing, as implemented in EPA-SWMM, can represent backwater effects, pressurized flow, and flow reversal. Hydraulic analysis identifies locations where capacity is exceeded and predicts water surface elevations. These outputs support flood risk evaluation and mitigation planning. But what about 1D versus 2D modeling? One-dimension models simulate flow along defined alignments such as pipes and channels. Two-dimensional models simulate surface flow across terrain grids, allowing water to spread over streets and topography. Coupled 1D, 2D models integrate underground conveyance and surface flooding behavior. FEMA and hydraulic modeling guidance increasingly reference 2D modeling for floodplain and urban flood mapping due to improved terrain data and computing capability. However, 2D models require higher computational resources and detailed input data. Urban flood mitigation strategies generally fall into structural and non-structural categories. Structural solutions, including enlarging pipes, adding storage basins, or modifying control structures. Green infrastructure practices such as bioretention and permeable pavement reduce runoff volume and peak flow. Distributed infiltration practices can increase effective storage and delay runoff. Regular maintenance reduces inlet blockages and preserves system capacity. Modeling allows engineers to evaluate the effectiveness of these approaches before implementation. So down below are the works we reference. And in conclusion, urban flooding results from the interaction of rainfall intensity, watershed characteristics, and infrastructure limitations. Both hydrologic runoff generation and hydraulic conveyance constraints contribute to flood risk. Drainage systems are designed using statistical criteria and therefore have defined limits. Hydrologic and hydraulic models provide a structured way to evaluate risk and test mitigation strategies. As with all modeling efforts, results depend on data quality, correct assumptions, and appropriate method selection. So thank you so much for watching this video. If you have any questions, leave it in a comment down below and we'll get to it as soon as possible. And check out our free EPA-SWMM course. Thank you so much for watching. And anyways, we will see you guys next time.